Let's talk about the oldest light in the cosmos, the faint afterglow of the Big Bang itself. Now this echo from the dawn of time, it should be perfect, right? A completely uniform glow, but it's not. And that one single imperfection, well, it reveals a pretty stunning secret about our own frantic journey through the universe.
So, I want you to imagine a photograph taken just a few 100,000 years after the Big Bang. That's basically what the cosmic microwave background, or CMB, is. It's this thermal radiation, this echo, that fills the entire sky. And for a long time, cosmologists expected it to be incredibly uniform, like the same temperature absolutely everywhere, down to the tiniest fraction of a degree. A perfect little relic from a much simpler time.
But it's not perfect. Not at all. This baby picture of the universe has a giant glaring flaw. If you look up in one direction, the sky is just a little bit warmer than average. And in the exact opposite direction, it's a little bit cooler. So what on earth could cause such a huge imbalance in the Big Bang's own afterglow?
And that question brings us right to part one of our cosmic detective story. We're going to dig into this strange flaw and figure out why this imperfection was such a massive, massive puzzle for scientists.
So you've got this smooth temperature difference, this gradient stretching from hot to cold all the way across the sky. Scientists have a name for it. They call it the dipole anisotropy. And for the longest time, it was a huge headache. I mean, did this mean our whole model of the early universe was wrong? Was the Big Bang itself flawed?
Well, the answer, it turned out, wasn't a flaw in the universe at all, but an absolutely brilliant insight about us. And this is where a physicist named Dennis Sciama comes into the story. He proposed this radical, almost unbelievable explanation way back in 1967, long before we ever had the tools to prove him right.
Get this, even before anyone had precisely measured this dipole pattern, Sciama had this incredible idea. He suggested that this background radiation wasn't just some passive, ancient artifact. No, he said it could be a fixed backdrop, a universal frame of reference we could actually use to measure our own motion. This was a revolutionary concept, the very idea of an absolute motion.
Okay, so to get how this works, we just need a quick refresher on something you already know, the Doppler effect. Think about an ambulance siren. As it races towards you, the sound waves get all squished together, right? And the pitch goes up. Then, as it passes and moves away, the waves stretch out and the pitch drops. Simple.
Sciama basically predicted that if we are moving through this ancient sea of light from the Big Bang, the exact same thing has to be happening. The light waves we're plowing into should get compressed, making them look hotter and bluer. And the light waves we're leaving behind, they should stretch out, looking colder and redder.
The theory was just beautiful, so simple and elegant. Those hot and cold spots in the sky weren't a cosmic flaw. They were the dial on our very own cosmic speedometer. All scientists had to do now was go out and prove it.
Now, the hunt for this dipole pattern took decades, seriously. Early experiments back in the 70s, some on balloons, gave these really tantalizing but kind of uncertain hints. By 1980, a bunch of different groups were seeing the signature more clearly. But the final undeniable proof, the smoking gun, came in the early 90s with NASA's COBE satellite, which mapped the entire sky with incredible precision.
And what's so cool here is you can literally watch science in action. The first measurements, you see they had these huge uncertainties. But as the technology got better and better, they all started to zero in on a very specific value. Every new experiment was telling the exact same story, just with more and more confidence each time.
So the crucial point here is this. The evidence was just overwhelming. That dipole pattern wasn't some primordial flaw from the dawn of time. It was us. It was the signature of our own movement through the cosmos, imprinted on the oldest light in the entire universe. And that confirmation, that discovery, it transformed the CMB from a simple baby picture of the universe into something absolutely incredible. A cosmic speedometer that could tell us exactly how fast we're traveling. Remember Sciama's bold prediction from all the way back in 1967? He claimed we could use the Big Bang's echo to clock our absolute speed. For decades, that was just a wild theory. But now the data was finally in.
And wouldn't you know it, decades later, the COBE data proved he had absolutely nailed it. By measuring the precise temperature difference between that hot spot and that cold spot, scientists could finally calculate our velocity relative to the rest frame of the entire universe.
So, what's the verdict? How fast are we going? The data shows that our solar system is hurtling through space at a mind-boggling 371 kilometers per second. That's over 800,000 miles per hour. And this isn't our speed around the sun or even around our galaxy. This is our speed relative to the universe itself.
And wait, because it gets even wilder. It's not just us. Our entire neighborhood of galaxies, what we call the local group, that includes Andromeda, is being carried along at an even faster clip, about 627 kilometers per second. And we even know where we're going. We're all heading toward a region of space marked by the constellations Leo and Virgo. Okay, so we know our speed and we know our direction, but this just opens up the biggest question of all. What colossal, unseen force is pulling us and our entire galactic neighborhood across the universe? The answer, in one word, is gravity. We aren't just coasting through space, we are being actively pulled. The theory is called gravitational instability, which is a fancy way of saying the universe isn't perfectly uniform, it's lumpy. And we're being pulled toward the biggest lumps out there, giant clusters and superclusters of galaxies, some we can see and some we can't. And this is really why this all matters so much. Our speed isn't just some fun trivia number, it's a clue. It proves we're part of this vast cosmic flow, like a river of galaxies all moving together. And by tracking that flow, we can start to map out the invisible gravitational structures that are pulling all the strings, revealing the true architecture of the entire cosmos. So, a simple flaw in what should have been a perfect picture has led us to this profound understanding of our place in the universe. We've used the Big Bang Zone echo as a speedometer, but it also acts as a compass, and it's pointing us toward cosmic mysteries like the Great Attractor and other massive structures we're only just beginning to get our heads around. The journey, as always, continues.